Alrighty. Let's see. So, for the people paying attention here right now, we have the class.
Yes.
Blade.
I said yes.
Oh. We didn't hear you say yes. Say yes. Or you better say yes.
Yes.
Thank you, Blade. Thank you. All right. Area. So approximate area under the graph function. This is what integration does. And right now we're going to approximate these areas by, when we draw it, we're going to draw little rectangles to estimate where this is. And this is going to eventually get to the point where we are creating the sum of those little bitty rectangles, all of them together, which is going to be equal to, it's like doing the limit functions. So as we get smaller and smaller and smaller, those rectangles keep getting thinner and thinner and thinner, which it eventually will just be the area of whatever solid we have there. It'll make sense here in a moment. So, right here, approximation area under the graph of a function. The area problems ask, given a function f, define and non-negative on a closed interval from a to b, what is the area A of the region enclosed by the graph of x? The x-axis, that is key, x-axis is the lower bound on almost all these. So, I lost my place. X-axis, and the vertical line, x equals A, x equals B. To answer the question posed in the area problem, we approximate area A of the region by adding the areas of a finite number of rectangles, as shown in figure 2, like we have right here. 1, 2, 3, 4, 5 rectangles, and we're approximating the area under that curve. This approximation, area A, will lead to the integral, which gives an exact area A of the region. We begin by reviewing formula for the area of the rectangle. Now, for this one right here, look very closely at this. Over and under is what I'm going to be asking. This first rectangle, is that an overestimation or an underestimation? Over. It's over. What about that one? Over. Could be over, could be under, right? Why? Because it's connecting right there in the middle, right? So it could be close. Okay. What about this one here? That one is clearly under, and this one is under. So I could tell by looking at it if it's going to be an overestimation or underestimation.
Does it have to get the concavity? Is it always an overestimation when it's concavity?
No, and it's gonna be depending on which type of function or what type of area I'm asking for. So, right here, graph the constant function f of x equals h for some positive constant h in a horizontal line that lies above the x-axis. Region enclosed by this, the x-axis, lines x equals a, x equals b is a rectangle whose area A is a product of the width, which is b minus a. That's important. B minus a, and the height, which is going to give me the h. And so my area is the height times whatever b minus a is. Okay? Are we okay so far? So, it's always my height is going to be the distance from the x-axis to whatever my function is. And my width is always going to be b minus a. Now, for this one right here, if y equals fx, constants of 3 horizontal lines, each of a positive height is shown in figure 4, area A enclosed by the graph of f, x-axis and lines x equals a, x equals b, sum of the rectangular parts a1, a2, a3. Okay, the total area would be adding each one, all of them together, right? Okay, so we would find whatever this is here. That would be basically my x1. This is x2, and right here would be an x3. And then I would actually have my h1, which would be whatever the floor function is there, or a ceiling function. This one would be like an h2, and this one right here would be an h3. So they're little rectangles, just based on type. So in this case, it would be x1 times h1 would be this first area. x2 by h2 would be that area. x3 times h3 would be that area there. And then I would have the sum of all those parts by adding them all together. All right, approximate area under the graph of the function, approximate area A, region enclosed by the function f of x equals, that is a 1/2 right there. Did it come out on your guys's, or is it still say 12?
Yes, 12.
Okay, so yeah, it's 1/2. So I don't know what happened. So when I copy it into the program, it sometimes renders it kind of choppy. 1/2 x plus 3, the x-axis, okay, so that means that's the floor. So the x-axis, unless otherwise stated, is always going to be the bottom. Unless stated, is always going to be the bottom. The lines x equals 2 and x equals 4. So that is my A, and that is my B. Now, let's do an overestimation. Let's make a rectangle using overestimation. I would use the 5, right? So right here, I would box that off right there, right? So my height in an overestimation would be 5. So for area for the first one would be 5 times b minus a, which is 4 minus 2, 10 units squared. Now let's do an underestimation. So the underestimation would use what?
4.
The 4, very good. So I would box it off right there, right? So 4 times my width, which is 4 minus 2, which is going to give me 8 units squared. Now, making the width 1. Making the width 1. So, you right here. There we go. Yes? Okay, you guys agree there, right? So the width is now 1, and so that's important because it's not just going to be b minus a, the width is 1, so it means that my x value down here is just going to be 1 instead of it being 2, right? So this would be 1, and this is also 1.
Why are you doing this?
I almost understood what you said.
Why are you doing this?
Why am I doing what?
It's related. Yeah.
Are you okay? All right, yeah. Because it says make W1, which is the width 1. Okay, so now we made that into 1. Redo it again. Overestimation. So I'm going to make a rectangle like this, and I'm going to make a rectangle like this. What is this point right here in the middle? 4 by 5. Times my width is 1, right? Plus this one over here, which is 5 times my width of 1. Where I get 9.5 units squared. All right, so that was the over. Let's do an under. So under would mean I would box it off there. So my height on this one right here would be, for this first one right here, what's the height? 4, yeah. 4 times the width of 1 plus right here, this height, which was 4.5 times the width of 1, which is going to give me 8.5 units squared. Which one do you think, which ones, in general, do you think are closer to the actual value?
Because the actual value is 9.
Actual value is 9. So you're saying that which ones are closest? The 3 and 4, right?
Yeah.
Okay. What do you think made that happen? What was the change that made it into becoming closer to the actual value? Making the width 1, or more rectangles. Dividing it up into more rectangles is going to give me a closer answer to what the actual answer is. Now, this one right here is kind of crazy here. So we're not going to do all these. We're going to do this second one. So this right here, you can see that's 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. No, wait, that's 0. 1 right there, okay. 5 subintervals. That's important for subintervals. So that means it's going to be 5 what? Very good. 5 rectangles. That's what I'm looking for. 5 rectangles. So how do I figure out the width of every rectangle if they're going to be equal? Okay. So divided by 10. Why'd you pick 10? Why would we pick 10 though? It's correct. But I'm trying to get you guys to make a formula out of this. That's the whole width, right? And how did we get that on our previous problem? B minus A, right? So you're saying, so for my width, so B minus A divided by N, where in this case the B minus A was 10 minus 0, so I have 10 right there, and I have to divide it into 5 subintervals, which is my N. So divided by 5, so each one, so 10 divided by 5 is 2. So that is the width of everything. So I'm going to go right here.
forgot the quotient rule. I forgot the quotient rule.
Quotient rule for derivatives?
Yeah.
Only because you're doing chapter 7. How can you forget that?
When you go through, you forget it backwards.
Oh my goodness. You're ridiculous.
Is
F prime G minus G prime F over G squared.
Okay, thank you.
If you were taking a test on derivatives, I would not give you that. All right. So we got our width. Okay, so lower sums. Okay, so now let's look at our first rectangle. Lower sum. What's going to be the height?
Zero.
Yeah. So technically, since I'm making the formula here, and I want you guys to see it like this, it should be f of the lower. So on this one, we have a function. So that's my height, right? So it's 2 times f of, in this case, 0. Yes? Okay, so now let's do the next rectangle. Plus, this one is going to go right here. Lower rectangle, so that's going to be 2 times f of what?
Wait, why would you put f of 0?
Which one's the lowest side?
Okay, so it's all 0. So then that would be 2 times f of 0.
Yeah, because it goes from 0 to 10. We didn't start at 1.
Mhm.
So right here, this is going to be an f of, what do we have here? 2. Plus 2 times f of, what's my next one going to be? Since this is concave up, all these are going to end up being on my left-hand side, right? So I could go through and draw each one of these rectangles. But if it was like a wave, I would have to alternate in between, right? Because I'm going to do lower sums for all these. So there's different ways of doing it. One's going to be a lower, so we're always going to pick the lower. Another one could be the upper, which we're always going to be the larger side.
Like a medium?
Huh? A little bit louder, please.
Is there like one in the middle?
Yeah, that's called the midpoint.
Is that what like, for like the one we did earlier, would that be like we were using the 4.5?
That would be the midpoint if we're using a rectangle.
Yeah.
Okay, but that's a slightly different, okay? So we would use that. It would be 4.5 as my height. So that's the midpoint formula. We haven't got there yet. There's also, since everyone's still paying attention, there is a left-hand side, which no matter the function, which one do you always pick? Say the left-hand side. What if we're doing a right-hand one? Guess which one we always pick? The right hand. So in the function, we are looking to see what it's asking for. This one specifically is saying all lower. So there is possible to actually say different things. And if you weren't taking a test over chapter 7-6 right now, I would give you the formula for the trapezoid rule. Okay? But certain people don't remember the formula for area of a trapezoid. I'm giving him a hard time. All right, so right here, we do this one all the way across. So keep going. So f of 4, 2 times f of 6, 2 times f of 8. Now, is that all of them? Yes. Because that is my 5 rectangles right there. So the first area should be easy. That one's 0. Second one. So that's going to be 4 times 2 is 8. My function's right here. That's the x squared. So that's what I'm plugging it into.
Isn't it 1 times 2?
Why do you keep getting 1?
Where did you get the 4?
What's the function? F of 2, right?
Yeah, at f of 2 is what? Oh. Okay, sorry, I didn't understand.
Wait, why didn't we put 2 times f of 10?
Okay, so count your rectangles. You ready? 1, 2, 3, 4, 5. This is the end point, so we're not going beyond that. If I had another rectangle, or if I had a right-hand side or an upper side, I would have this one here, but I also wouldn't use f of 0. So if you count up your rectangles are going to be what it is that you're looking for. Okay? All right, so next one is f of 4, which is 16 times 2 is 32. 36 times 2 is 72. And 64 times 2 is,
128.
yep. Add those together. What's that? 40, 80, that's 30, 132. 240?
40,
Does that make sense?
Yeah.
It's geometry, and it's bunches area. So we're gonna leave off there and have a couple problems for the homework. You guys already looked at the homework, right? We'll continue this tomorrow, and hopefully I will have the rest of those people in here tomorrow, because tomorrow, if you are not here for the test, you don't get the test, because I need to grade the test, I need to give it back so you guys could actually go over it, but, you know, we have so many people that don't show up anymore that I'm not going to wait on them. So, all right. Huh?